All right, let's jump right into this. Today, we're diving into the invisible system that makes real-time AI conversations actually practical. Because, if you've ever used a large language model, you've actually witnessed this fascinating, almost cinematic mystery play out right on your screen, probably without even realizing it.
Picture this. You type this big, complex prompt into ChatGPT, right? And you hit enter. Then, there's that strange, noticeable pause. It kind of feels like the system is, thinking? But then, boom, that first word drops, and suddenly the rest of the words are just flying across the screen at lightning speed. So why did the AI suddenly become so much faster? Well, figuring that out reveals literally one of the most important engineering breakthroughs in modern AI.
Okay, to make sense of this, we need to look at two totally distinct phases of AI text generation. First up is the pre-fill phase. This is the slow part. The model is essentially reading your entire prompt all at once. It's crunching thousands of words in parallel to grasp the context. It's just a massive, heavy computation. But the second it spits out that very first word, it shifts gears into what we call the decode phase. Here, it's generating text just one word or token at a time. And this phase is shockingly fast. So let's look at exactly what's going on during that weird initial delay and why the decode phase doesn't suffer from it.
Chapter 1. The Strange Delay. Moving right along to Chapter 2, Why AI Keeps Repeating Itself.
So, to solve our little mystery here, we have to look at how early language models were built because, honestly, they had a pretty massive, crippling flaw. They relied on this process called autoregressive generation, which basically means every single new token depends on all the previous ones. So, let's say the model generates the word the. Cool. To get the next word, cat, it has to read the. But to get the third word, sat, a naive model has to start entirely from scratch. It rereads the, then reads cat, just to predict sat. It's like, imagine a teacher taking attendance for a class of 100 students. When the 100th student walks in, the teacher doesn't start over and recount the first 99 students, right? That would be crazy. But without optimization, that is exactly what an AI does. By the time it spits out the 1,000th word, it has literally reread that very first word 1,000 times.
And this creates a brutal mathematical bottleneck. It's what engineers call an O(n)² complexity. Basically, the longer your conversation gets, the slower the math becomes, until the whole system just grinds to a halt. So to fix this, engineers had to bring in our hero, this incredibly clever optimization known as the key value cache, or KV cache. It completely stops the model from recomputing what it already knows. Which brings us to Chapter 3, the hidden memory.
Okay, to see how this actually works under the hood, we've got to look at the transformer's attention mechanism. Inside the model, every single token is transformed into three vectors: a query, a key, and a value. Think of it kind of like a giant library. The query is the specific question that the current token is asking. The keys are like the titles on the spines of all the books. It's how other tokens identify themselves. And the values? Well, those are the actual contents inside the books. Now, as the model generates text, the query changes with every single new word. But, and here's the brilliant part, the keys and values for past words never change. Once the word cat is processed, its key and value are locked in forever.
So, that brings us to the golden rule, our absolute core mantra here. Never recompute what you already know. During that slow pre-fill phase we talked about earlier, the model does all the heavy lifting. It computes the keys and values for your entire prompt just once, and then tucks them safely away in a dedicated high-speed memory block, the KV cache. Then, during the super-fast decode phase, for every new word, it only computes the fresh query, retrieves the old keys and values from memory, and just appends the new ones to the end of the list.
You can actually see how the data flows right here in the pipeline. The input token fans out, and those keys and values are safely tucked away into their respective caches. The query just checks that cache to produce the output. It literally turns a massive repeating computational nightmare into highly efficient incremental generation. And there you have it. That answers our opening mystery. The AI isn't actually thinking faster during the decode phase. It simply stopped doing redundant math. Without the KV cache, modern conversational AI would be agonizingly slow, just completely collapsing under the weight of its own computation. With it, we get that instant, snappy text generation that makes these chatbots feel like pure magic. But, as with all things in engineering, this brilliant solution came with a massive catch.
That takes us to Chapter 4, Engineering AI at Scale. See, we totally solved our math problem, but in doing so, we accidentally created a terrifying new bottleneck. We essentially traded a compute problem for a memory problem. Consider this number for a second. 83 gigabytes. If you're running a big 70 billion parameter model, like Llama 3.1 for example, and you're serving a batch of just 32 users with an 8,000 token context window, 83 gigabytes is the amount of precious GPU memory required just to store the KV cache. That is actually more memory than the model weights themselves need. It's wild.
And this reality triggered what we call the great pivot in AI infrastructure. AI inference has fundamentally shifted. We are no longer compute-bound, meaning, we aren't limited by how fast the math processors are anymore. We are now totally memory-bound. The speed limit of AI today is dictated almost entirely by how fast we can shovel massive amounts of cache data across the GPU to feed the processor.
So, to keep this memory monster fed without crashing servers worldwide, engineers have had to get really creative. They developed things like grouped query attention, which forces multiple query heads to share a single KV cache pair, drastically reducing its overall size. Then there's quantization, which physically compresses the cache into smaller bit formats. But honestly, one of the most elegant solutions borrows a trick directly from standard operating systems.
It's a clever optimization called PagedAttention. See, early systems used to just reserve a massive, continuous block of memory for the maximum possible conversation length. But if a user only typed a few words, up to 80% of that memory just sat there, totally empty but locked up. PagedAttention fixes this by dividing the KV cache into small, fixed-sized blocks, say 16 tokens each, and allocating them strictly on demand. It virtually eliminated memory fragmentation, cutting all that waste down from 80% to under 4%. Just a massive game changer.
And for data that just flat out won't fit on the GPU, researchers are designing these incredible hardware-software orchestrations, systems like InfiniGen, LayerKV, and CLO. Check this out. While the GPU is busy computing one layer of the neural network, the CPU is already prefetching the cached memory for the very next layer and sliding it over. It's this beautiful, perfectly synchronized assembly line designed to completely hide the latency of moving all that data around.
So what's next? Let's look at Chapter 5, the future of AI memory.
Where is all of this heading? Well, as context windows explode from thousands of tokens to literally millions, the absolute frontier of research right now is extreme compression. Upcoming technologies like Google's TurboQuant and NVIDIA's KVTC are pushing the very limits of physics. They're figuring out how to compress the KV cache by up to 20 times using crazy techniques like transform coding and polar coordinates, and doing it all with near zero loss in the AI's actual accuracy. This means, very soon, AI models will be able to remember exponentially more context without needing bigger, more expensive servers.
It's amazing to think that what started as a simple math trick is now evolving into this massive multi-server infrastructure layer. Soon, KV caches won't just live on one single GPU. They're going to be distributed across entire clusters. The systems will intelligently route your chat request straight to the specific server pod that already holds your conversation's cache right in its memory.
Which really brings us to the core takeaway of this whole explainer. Next time you hit enter and marvel at the speed of those words appearing on your screen, remember this: the AI wasn't thinking faster. It simply stopped repeating expensive calculations. Faster AI isn't always about brute forcing better models with more math. Sometimes the greatest breakthroughs come from simply finding smarter ways to remember what has already been computed. And I'll leave you with a fascinating question for the road ahead. As these context windows stretch to millions or even billions of tokens, the whole challenge shifts. We already know how to cache the past, but what else can we teach these machines to remember? And maybe, more importantly, to be truly efficient, what can they afford to forget? Definitely something to chew on next time you're chatting with an AI. Thanks for exploring the hidden memory of ChatGPT with me today.